A nuclear half-life is a measure of decay in a nucleus. So what it says is that after one half-life, which is a measure of time, half of the nucleons have decayed away, and these are inside the nucleus. Okay, so if we have 1,000 nucleons, after one half-life we would have 500, after another half-life we would have 250, and so on. Okay, so after one half-life, 25% of the nucleons remain. Remember, the nucleons are the protons and the neutrons. After two half-lives, however long that is, 25% are left. And after three half-lives, 12.5% are left, and so on and so forth, until I guess we can't measure them anymore. So this is a constant property that's going on inside the nucleus over time. Notice that we cannot predict exactly which nucleon is going to decay. The only thing we can predict with a great deal of certainty is that after a half-life, half of them are gone or have decayed downwards. So the half-life is the time required for the number of undecayed nuclei, the activity or the count rate of radioactive sample, to decrease to half of its original value. Okay, best way to show that is by some examples. So in this example, we're told that a sample of phosphorus 32, so phosphorus 32 phosphorus. Yeah, just check phosphorus is indeed P. So phosphorus 32 has a half-life. Now I'm going to put half-life as half, as time, T, and then underscore that by half, meaning half-life. Okay, and the half-life of phosphorus 32 is 14 days. So it's okay to leave half-lives in days or years. I know that the standard unit for time is seconds, but if we're dealing with millions of times, it doesn't really make much sense to convert it into seconds. If you start with 400 grams, so the amount 32 is 400 grams, and we're going to leave it as grams rather than convert it to kilograms. What will be the mass after 42 days? So it's going to half in mass every 14 days. Now there's a couple of ways of doing this. We could work out how many half-lives that is. 42 days divided by 14, it's going to be some number. Let me grab my calculator. So 42 divided by 14 is going to be 3 half-lives. So 3 half-lives is what we're going to have. So we're going to start with 400 grams, and that's after 0 half-lives. After 1 half-life, it's going to be 200 grams. After 2 half-lives, it's going to be 100 grams. And after 3 half-lives, it's going to be 50 grams. That's one way of doing it, just doing it pretty much by guess and check. The other way of doing it is to use the formula. So the amount of a substance as a function of time is going to be the amount of the original function when time is 0 times half to the power of the time that's elapsed divided by the half-life of that element. Okay, so this is the original amount. This is the amount at time t. Obviously, half is half. This big T, this T here is the elapsed time. And this one here is the half-life of that element or substance. And T and half-life have to be in the same scale. So it doesn't make much sense to have 3 seconds divided by 5 years. Okay. That is our formula that's going to be doing most of the work. The next question asks us to work out how long something will take if it has a half-life of 5 years to go down to 1/16 of its original value. There's the easy way and the hard way. We could do a table. So here we've got time, and here we've got, let's call this M for mass. So time 0, the mass is 1. At time 1, it's half that. So half of 1 is half. After 2 half-lives, we're down to a quarter. Half divided by 2 is quarter. After 3 half-lives, we're down to an eighth. After 4 half-lives, we're down to a 16th. So after 4 half-lives, we would be down to 1/16, but each half-life is 5 years. So it would be 4 times 5 years, which would be 20 years. Okay, how would we do this mathematically? Let's go into the original equation. We've got 1 over 16 is what we've got at some time. And the half years are 5, so it's going to be equal to the original amount, which is 1, times half, and then the time divided by 5 years. And now we want to solve for t. So this 1 is going to factor out. So 1 over 16 is going to be equal to 1/2 to the power of t over 5. How are we going to do it? We're going to need to use logs. So the natural log of 16 is going to be equal to t over 5 times the natural log of 1/2. So the natural log of 1/16 divided by the natural log of 1/2 is going to equal t over 5. We're going to cross multiply that 5. So the t here is going to be 5 times the natural log of 1/16 over the natural log of half. And I hope when you do that, you should get the answer as 20. Okay, let's do another one. But if you're interested, I put them in the calculator here, and I did get 20. Okay, the next question asks us to find the half-life. So radioactive samples activity drops from 3,200 becquerel, which is a measure of radioactivity, to 200 becquerel in the space of 12 hours. So radioactivity falls as as a half-life. Calculate the half-life of the sample. Okay, let's see how many half-lives it would need to take it from here to here. Let's just do it by table. So time equals 0. The mass is 3,200 becquerel. It shouldn't really be mass. Let's call it N. After one half-life, it's halved again. It's halved. What's it going to be? 3,200. It's going to go to 1,600. After two half-lives, it's going to be 800. Three half-lives, it's going to be 400. Four half-lives, it's going to be 200. So 4 half-lives in that 12 hours. So therefore, the half-life of this is going to be 12 hours divided by 4 half-lives. So that's going to be 3 hours. And let's see if we can work it out. All right, for this one, we're asked about percentages remaining. So we have iodine 131. It's used in medical treatments. It has a half-life of exactly 8 days. So T half equals 8 days. What percentage of the original radioactive iodine 131 will be left after 24 days? A couple of ways we could do this. The best way to do it is to find how many half-lives is that. How many half-lives is that? And the way we're going to find that is the total number of days divided by 8, and obviously that's going to be 3. So in other words, we're saying how much of this iodine 131 is going to be left after 3 half-lives, and then present that as a percentage. We could do it as a table. So time t equals 0, 1 half-life, 2 half-lives, 3 half-lives. When we begin, there's 100% there. After 1 half-life, there's 50% there. After 2 half-lives, it's going to be 25% there. And after 3 half-lives, there's going to be 12.5% left. And that's all that's going to be left. Let's do that on our little graphy thing that we have. So the original amount, let's say we've got 100%. The final amount, we don't really know. The time elapsed is going to be 24 days. The half-life is 8 days. Let's calculate it. And yep, sure enough, there is going to be 13 grams left, and it's going to be 12.5%. So it's rounded a bit. The remaining 12.5% is what we've got. 3 half-lives. How about that? This is a nice little question. Working backwards, a scientist measures the activity of a sample to be 150 counts per minute, CPM. The half-life of this material is known to be 10 minutes. What was the activity 40 minutes ago? 40 minutes if time now is 0, and time in 10 minutes is time equals 10. Time 40 minutes ago was minus 40. Now trust me, because this does actually work. So the time of minus 40, and when time is minus 40, is going to be what it is now, 150 times half to the power of minus 40, and the half-life is 10 minutes. So 150 times half to the power of -4 is going to give us something interesting. Let's get our calculator, clear that out. So, E times brackets 1/2, close brackets, to the power of -4, 2,400. Remember, a fractional number to a power of a negative number is the same as the reciprocal being raised to the positive power. So that means that it was 2,040 minutes ago. Okay. Another way we could have worked it out is by doubling it. So at time equals 0, there are 150. At time after 1 half-life, there would have been 300. 2 half-lives, there would have been 600. 300, and that's how many half-lives there are if in 40 minutes if the half-lives are 10 minutes. 40 minutes divided by 10 is 4. So in 4, it's going to be increased by that amount. There you go. All right, in this question, radiocarbon dating, carbon-14 has a half-life of 5,730 years. An ancient wooden artifact was discovered and was found to contain 2.5 grams of carbon-14. Scientists determined that if the wood were fresh, it would have contained 20 grams of carbon-14. Calculate the age of the artifact. So I guess the inference here is that all of this missing wood is the result of radioactive decay, carbon-14 becoming nitrogen, etc. It hasn't been eroded back, but we won't go there. We'll just presume that all of it is being because of radiocarbon decay. Okay. So what have we got and what have we got to work for? So our original amount we've got is 20 grams. And our end amount is 2.5 grams. And we know that the half-life, the time it takes for half of it to decay, is 5,730 years. All right, let's do a couple of things. Either we can do it by hand. We could say, okay, so time times 0, there is 20 grams. After 1 half-life, there'll be 10 grams. After 2 half-lives, there'll be 5 grams. 3 half-lives, there'll be 2.5 grams, which is what we want. So it's 3 half-lives, which would be 3 times 5,730 years, which is a lot. Or if it's not this really nice number, we can put the numbers into our original equation. So the amount that we've got now is 2.5 grams, and that's going to be equal to the original amount, which was 20 grams, times this half over the time that's taken, divided by the half-life, which is 5,730, and then we would solve that for t. We would put it in our calculators and solve it. In fact, I'll do that one first, and then I'll show you how you would do it using the logarithms. So we have our amount here. Let's go to the equation solver. Go to solver. Let's delete everything else that's here. 2.5, and then shift equals 20 times brackets 1 over 2 close brackets to the power of brackets, and then x is what we're looking for, divided by 5730 close brackets, exe, solve it, 17,100 so 790 years. Okay, excuse me. Or we could use logarithms. So we could take this 20 over here. So 2.5 t. This should be a really nice number. 5 divided by 20 is 0.125. So 0.125 is going to be equal to, we can take the log, t over 5/7. So the natural log of that is that times the natural log of half. So the natural log of 0.125 over the natural log of half. They're both going to be negative numbers, and it's going to cancel out. And we want to multiply that 5,730, and let's see what we get. We should get the same number. So on the top, the natural log of 0.125 close brackets times 5730 equals that. Divide that by the natural log 0.5. We get the same number, 17,000, same answer, 3 different ways. All right, so this is a bit of a trick question. So we have a Geiger tube, a Geiger counter, measures radiation from a radioactive source. So far, so good. The initial measured radiation is 430 counts per minute. We're told, though, that the background radiation, that's the radiation that we all live in all the time, is measured separately at 30 CPM. If the half-life of the source is 2 hours, so the half-life there is 2 hours, what will be the total reading on the Geiger counter after 6 hours? By 2, that's going to be 3 half-lives. Okay, can you see the little trick here? What is the actual radiation that we're measuring from this radioactive source? It's not 430, it's 400, because 30 is the background radiation. So our initial radiation is going to be 400. And then if we half that, 3 half-lives, after a 1 half-life, it's going to be 200. After 2 half-lives, it's going to be 100. And after 3 half-lives, it's going to be 50. So that is the main radiation. What about the background radiation? Does that fall? No, the background radiation stays constant. So it's 30 there, it's 30 here, it's 30 here, it's 30 here. So the total radiation will be 80 counts per minute, whereas 50 is the radiation and 30 is background radiation, which is really hard to get rid of. And that's that. So for this last one, we're told that isotope A has a half-life of 5 hours, and isotope B has a half-life of 15 hours. Both samples initially start with the exact same number of radioactive nuclei. Okay. After 30 hours have passed, how many times more radioactive is the nuclei of isotope B compared to A? Okay. So let's look at A and B separately. And let's say they both start off with, say, 1,000 nucleides. So the half-life of this, so the half-life of A is 5 hours, and the half-life of B is 15 hours. And the time for both of them is 30 hours. So for A, the number of half-lives that A is going to undergo is going to be 30 hours divided by 5, which is 8. And B, the number of half-lives it's going to undergo is going to be 30 divided by 15, which is 2. All right. So let's put this into our little machine thingy that we've got. So the initial value here, this is for the first one, is 1,000, and the half-life is 5 hours. The time elapsed is 30 hours. The half-life is 5 hours. I'm going to calculate. So there are going to be 16 nucleides remaining of the first one. So there's going to be 16 of this first one, and this other one is going to be pretty much easier to do. We just need to halve it. So after one half-life, it's going to be 500. After 2 half-lives, it's going to be 200. Oh, there is going to be 250 divided by 16 times as many B as A after 30 hours. And what is that as an actual number? So 250 divided by 16, 250 divided by 16. So there's going to be 15 times as many B as A, because A is decaying much, much, much faster.
What just happened?
I fell out.